Okay, so first of all, I'm really glad to be a part of CakeFest again. This is not my first CakeFest. The first one was over 12 years ago, 2008 in Orlando. That was a long time ago. That was the first official CakeFest, actually. So I'm really glad to be a part of it again. Of course, I would have loved for this to be an in-person event somewhere around the world, as is the common thing for CakeFest every year. But this is 2020, so it's going to be very interesting and exciting to do this whole thing remotely. I'd like to thank and congratulate and give kudos to everyone involved in the organization of CakeFest. I know how hard it is to organize in-person events. I can only imagine how much harder it is to do this whole thing remotely and virtually, having to deal with time zones or speakers like myself that don't answer emails. So it's very challenging, I'm sure of it, and thank you from the bottom of my heart. I decided to pre-record this talk because I live in the southern coast of Argentina, in a very small city, where internet connection speed is not precisely our biggest asset. So doing this whole thing in real life would have been quite challenging, if not impossible. So the topic at hand, or the topic that I'm going to be covering here, data-oriented development or design, is a topic that got me excited a little bit about over 2 years ago when I first discovered it, because it has a completely different attitude compared to other proposed different way of doing software development, such as aspect-oriented programming or object-oriented programming or domain-driven development and all that. Whereas most of those paradigms or way of thinking in software development evolve around modelizing and how to translate into code the problems that we're dealing. DoD in particular makes a completely different take, in the sense that it makes no assumptions. It doesn't consider established beliefs to be the absolute truth in the industry, and takes a completely different approach in a way that goes in line with what Simos is eloquently saying here about having an open mind towards our own limitations when we make software development decisions, realizing that we are actually total idiots. So that helps a little bit to not be a total idiot. So these wrong assumptions have been actually polluting the software development industry for decades, because they have been an integral part of pretty much any school of thought regarding the programming world. Most of the time, we are taught that object-oriented programming is the best and ideal and the best possible way to modelize and implement solutions to coding problems, because it's somehow about taking into our real-life concepts as close as possible in code. So when we read the code, we know exactly how it maps to the real world, and somehow we've been taught that that's the perfect way. We've also been taught that for some reason data redundancy and data storage is so sensitive that we even at one point a few decades ago decided that it was because of saving just a couple of digits out of the year. We thought it was worth risking planes flying down from the sky during Y2K. We are also taught that hardware is not important unless we are particularly developing for hardware. Somehow we're taught that hardware is so cheap that it should not even be a factor in our decision-making process when we are doing software development. And these wrong assumptions, they were carrying over and over through our different evolution as programmers, particularly in the PHP world, as we went through a kind of mess of include files and procedural code towards a more organized and modelized abstraction of the problems through object-oriented programming, where the focus was precisely and purely on abstraction. We then decided, okay, now that when we need to render this abstracted logic that I have in my classes, in my object-oriented programming code, how do I do it without actually polluting all this nice abstraction with all my view code? So we decided to layer it down to separate the view from my business logic, and having this controller interacting or sending information back and forth, so to make everything a little bit more separated and more manageable with. But the more layers that we added, we realized clearly that things started to break more often. So we decided that, okay, now we need to focus on our code not breaking. So the main focus became expectations, or at least the expectation of what we believe is the right way to run our software, or what we believe is the correct way for it to run. So we focused, we deviated the focus away from abstraction and presentation and laser focusing into expectations. We then decided, okay, now this is getting even more complex, and we completely lost track about the business logic, to the point that we're thinking about developing tests first and dealing with the expectations way more than the problem that we're actually trying to solve. So we lost track of business logic, and we decided, okay, we need to rethink this, and through domain and make domain knowledge a big part of our work. So we even added more layers to the problem, and all this evolution has been all circling around the same basic assumptions and the same basic idea that the most important thing a software developer has to do is modelizing the problems in real world code that we can read in a human-like fashion. However, there's this thing that started happening a few years ago, where the game dev industry, which is an industry unlike any other in the software development world, because they work with completely different set of constraints and limitations compared to us, web dev developers. It started happening that these established schools of thoughts and way of software development, such as object-oriented programming and all this other stuff, didn't play nice with the limitations that are so characteristic of game dev development. In a game dev world, performance is not only a major driver in the work that they do every day, but it also defines the success or failure of a product. It's so much so that it is an identified characteristic how well a game runs by the number of stuff that it can do in a single second. And when we play games, that may not be very evident to us, but when we dive a little bit into how games are built, it is quite remarkable the amount of stuff that has to happen in a single second. I love this talk in particular, that given by Marty Walsh at GDC 2014. But I love this slide in particular because it kind of gives a glimpse into everything that might be happening when we're playing a single game. On this case, a first-person shooter where an agent is clearly entering an area where that agent has to think about a lot of things. It has to somehow modelize the ability to see not through objects, but to see around objects and see all the nearby other agents and other characters in the game that may pose a threat to me or not. It has to also somehow modelize the ability to hear and hear sounds. If there's a gunfire nearby, clearly the agent has to respond to that. It also has to deal with a lot of decision making in the process through behavior trees or other means of making these decisions, such as should I engage in combat with a possible threat, or should I go find a cover spot, and then I need to find what's the best cover spot depending on where the threat is coming from, and all that has to happen in a single second. So imagine that for a single agent multiplied by many agents, and now suddenly hardware, memory, all that stuff that we've been taught that is not precisely important in our day-to-day until they become a problem, are major sources of concern for the game dev industry. So clearly, established principles that are so prevalent for us developers don't play nice with game dev. So something started happening in the game development world where they started to reimagine things. And one of the most prominent defenders, if not considered to be one of the founding fathers of this new school of thought, is Mike Acton. He's not surprisingly a person out of the game dev development world. He works at Unity right now. And his take is completely different. He actually makes a whole statement about how we've been taught the wrong things. He calls it the 3 big lies of software development. Go search, go Google it. He has a very interesting blog spot regarding these 3 big lies. His whole idea or his whole take on this is that we've been thinking about programming as software programmers completely the wrong way. We've been thinking about abstraction and modelizing problems and not about the actual stuff that we're doing, which is transforming data from input to output. So our job as developers, says Mike, it is purely to transform data from input to output. It's not only his take. There are other prominent members mainly in the game development industry that also second this thought. Christopher makes I think the most clear statement regarding DoD, data-oriented development, which is positioning it as completely the opposite of most other programming techniques, in that DoD doesn't deal with abstraction at all. It actually it tries to fight abstraction by focusing purely on the data and the work that we do on that data. So the whole idea behind DoD is to focus primarily on data, have a laser focus on it, and work on the transformation. And when I say work, I don't necessarily mean code. One of them, the many things or many benefits that DoD brings to the table is that we rethink a lot of processes, and sometimes that rethinking process may mean that it's not about actually coding something; it's about transforming it through other means. Now, when DoD came to be around 2009, 2010, obviously it was a necessity to seriously improve the performance of games and game development in general. So performance is clearly a very implicit part of DoD, but somehow when we go through this process of learning DoD, we tend, as web developers or mobile developers or other kinds of developers who are not game devs or satellite programmers, we don't think performance plays a major role, because we've been taught throughout the years that performance is an afterthought, or is something that needs to be dealt with only when it actually becomes a problem. And most of the times when we reach that kind of thinking, we are taught, or we're quoted that famous Donald Knuth quote about premature optimization being something really bad. And thinking about performance improvement before you actually build something is not the right way to go towards things. And one of the things that I only learned recently, and I thought it was quite remarkable, is that it's actually a misquoted or a misinterpreted statement, because it came originally the first time that it was published, it was in a paper or in a magazine or a book, I can't remember now, around 1974, that it was about defending the use of goto, which is precisely the opposite of what we expect this statement to be all about. It's not about not optimizing for performance, it's about optimizing the right, in this case, what he says here, the right area of our application that may have a big impact. And it's understandable that we have not been focusing on performance much, because hardware has been throughout our evolution as programmers become quite a cheap commodity. So we don't even think about it. We just throw servers at the problem. We throw more hardware, so we don't have to think about memory or anything that may affect our day-to-day works. And because essentially this whole evolution of software prices and manufacturing made us lazy as programmers. So DoD, even though it is implicit, I make it explicit by saying that it not only asks us to focus primarily or almost exclusively on the data and on the stuff that we do on the data, but it's also about making it as efficient as possible. Another thing Mike likes to say on his several talks where he covers this subject is that for some reason we are taught that doing something the most efficient way is not necessarily a good thing, which is kind of insane. Why would it not be a good thing to make something run as fast as we can? So I like to take his quote and modify it a little bit to introduce, to make sure that when we are indeed transforming data from input to output, we do so in the most efficient way possible. Obviously, possibility being a major key, because we cannot speed up what we cannot speed up. So in order to identify that 3% or that area of our application that if we improve we improve the performance, it's going to have a big impact, we clearly need to know that what we are dealing with. We need to go into our application and actually measure stuff, because following our own assumptions regarding what's performant or not performant can lead us to tricky or definitely wrong conclusions. There's Andre has this talk. It's actually a two-part talk. It's very long. It's one. I think the first part is about 1 hour and 30 minutes, and the second part is another hour and 30 minutes. So a good old 3-hour talk, which is one of my favorite dissertations. That it's available on YouTube. So go search his name. It's clearly it's gonna pop up on the very first few results, where he's talking about particularly on the C++ area about performance improvement, but he makes a whole introduction about how our assumptions about what's performant and what's actually what works faster or not is completely, at least for me, and I think for most people there at that talk, it is completely mistaken and wrong. And so his whole attitude towards it is the right attitude, which is we need to measure, we need to understand and reason about the code that we're working with to make sure that we take that very important and involved effort into optimizing the right stuff and not the wrong stuff. And when we measure, there's a lot of stuff that can get in the way if we are not laser focused about finding that data, finding that area of possible potential improvement. And he has this little format which I think is very clear and very clear, where he says, okay, we clearly, when we are trying to measure something, we're trying to measure application, we have the stuff that we need to measure, which is the T, the stuff that we're trying to measure. But there's also all these other times there that are part of the transaction or that we're measuring that add a lot of noise to our possible potential conclusions. We have the overhead times of calling a function in PHP code or creating an instance of an object. We have all these added noise of the networking speed, waiting for a file system read or write, and we have quantization noise, which is essentially the resolution of the machine, how exact a measurement can be done, which is normally in the microseconds, which seems like it wouldn't be a factor because it's just microseconds. But the more we measure and the more times that we're adding up, that quantization noise tends to also add a little bit of noise and may drive us away from the right areas of improvement. So his whole take on this is that instead of measuring time, we should measure relative improvement. So it's not about if I reduce or I improve from 150 requests per second to 165. It's about that I improved 35% towards whatever I was doing previously, because doing it relatively or doing time comparison this way allows us to cancel all this noise out. So to actually take on Andre's take, to use Andre's take and see a little bit about how our misconceptions about and these wrong assumptions that we've been following as software developers can lead us to wrong conclusions and put effort in the wrong place. I decided to do this little completely unrealistic and not real life example where I have this world this world where I put agents all over the world, where some of those agents can be friendly to me and some of those agents are actually a threat. And for those agents that are a threat, that are my enemies, I may find enemies that are tougher to beat than others. I may find enemies that are not even beatable. And I may find one big arch enemy, which is the most, the toughest of them all, the actual boss in my little world. In order for me to actually reason with what constitutes an enemy or not, I have the concept of me being a player having my own bullets. So if I have more bullets than an enemy, I clearly can defeat them. If I don't, I clearly cannot defeat them. So in the standard way of object-oriented programming, following the assumptions that all the stuff that we've been taught and that we've been using all this time, all these years, throughout our progression as software developers, this is clearly something perfectly OOP that speaks, okay, this is right and beautiful code, this is a very nice abstraction and human readable, where I totally can relate the stuff that is on that little graphic, where I have my enemies, where I have my agents that could be enemies, that I could kill, and I have a certain name and a number of bullets, and seeing this abstraction clearly speaks about being able to transfer the real life concept that I'm trying to solve into actual code as close as possible to those concepts. So here I'm just filling out the world and going through these as many agents that this program or this system wants me to have. So I have all this world of available rows and columns, and I fill those rows and columns with as many agents as I'm told, and giving those agents for those agents that I decide to be enemies, giving them any number of bullets between 0 and this maximum number of bullets. And I do some AI logic here to decide if an enemy is an enemy just by saying that if they fall in an even row and column, then they become enemies, otherwise they are friendly to myself. So I do, again, this is 100% in line with the modelization or abstraction that we saw of agents, and we fill those agents, we create them, and we fill them in a neat multi-dimensional PHP array where my rows are my rows and my columns are my columns, again abstracting and making evident the real life problem that I'm solving into the code. So this is clear, this is all great, and I feel that. And obviously this algorithm is gonna fall to, I'm seeing that now, it's gonna fall to pieces if I'm asked to place more agents than there are available cells. But yeah, I decided not to account for that. So the first thing that if I look to, if we are trying to find how many enemies I've got, and of those enemies, which one is my arch enemy, based on the modelization of the problem that I had made, is clearly again 100% OOP and super approved by our established school of thoughts, then this is perfectly valid. I go through all the columns that I have in my world, and then I go through all the rows, and I go in each cell by cell, and looking into if there's anybody there. If there's not anybody, obviously I skip it, and if there's anybody, then I'm interested in seeing if it's an enemy that I can kill, and if so, I figure out which one is the arch enemy just by counting how many bullets they have. The enemy with the most amount of bullets is my arch enemy, and I count the enemies, and that's it. And this is the whole intention of the algorithm. This obviously is not the most profound thing, because we are also taught that a 4 of a 4 is not the best performing piece of code, but this is in terms of what OOP and other schools of thought define as good approaches to modelizing software problems. This is perfectly valid and perfectly acceptable code. So if I run it and I create a world of 5,000 times 5,000, so a lot of cells to be filled with 20,000 agents there and a maximum of 5,000 bullets, and I design myself to have a random amount of bullets, I can run it. I do this very scientific measurement of time to run it, I think, 5 times, where I assume that the code is working correctly. I see different situations where I got more or less bullets, and based on that, I get more or less enemies. You can see a pattern where the number of bullets that I have versus the number of bullets my arch enemy has is always -1, and this is because I had so many agents to fill in and so little bullets that it is likely that the randomness is not the best possible, the best take at having different bullets for my arch enemy. But it is clearly working. I assume that this is a good time, 1 second, 1.10 seconds. We normally would have been taught, or we are taught, that since this is perfectly valid code, that we can reason by looking at the code and realizing just how closely it resembles my real life problem, then this is perfectly valid, and we would have been content here. So, but let's take this Andre's approach into not believing our own assumptions regarding performance, and it's just for the sake of it switch these 2 lines around. So instead of going when I'm looking at my enemy, counting my enemies and finding the arch enemy, instead of going first column by column and then row by row, I'm gonna switch that order around, and then I'm gonna go row by row and then column by column. Just making one simple change that, again, the school of thought of programming would will have no opinion regarding this fact because it makes absolutely no difference. The logic that I'm reading is exactly the same. It's only different. The only difference is how I navigate the world. But I wouldn't expect as a software developer for this to be a major source of change for my program. The program is doing essentially the same. So if I run it, now it's a completely different scenario. Instead of going from 1.09 seconds, we shaved off. We made the whole algorithm 63% faster, and simply by changing the way that I navigate through my world. And there's obviously there are reasons behind it, but the main take that Andre people like Andre tries to teach us when we are trying to break assumptions regarding performance is that we need to start reasoning about the hardware that we are running the stuff on. On this particular case, I know that I have this again, I have this world where I have my little cells and I place agent on those cells. Each of these beautiful boxes are essentially my agents that store different the data that is part of my implementation of the interface that we define. So an agent has a boolean indicating if it's an enemy, it has a name, it has a position, it has the number of bullets, and I have in my PHP array obviously all these agents neatly placed on memory, one element after the other. The problem is that when I navigate by column, just going from top to bottom and then from top to bottom and then from top to bottom, I am clearly fetching the elements that I want. So I'm dealing with the first element and the second element, but there's something going on behind the scenes in the hardware that we're running in it on. And essentially, when I'm looking to fetch an agent from my matrix of agents, of cells that have agents in them, clearly the software has to somehow go into RAM memory, into the memory, storing all those agents, fetch that and return it to me. But another thing that the hardware does behind the scenes to try to make our jobs easier for the next time that we're doing this, if we are indeed going through the different agents in our world, is try to figure out what is the next agent that we're going to work on. So it does so using cache lines. There are different types of cache in the hardware where it loads the required agent, in this case the first agent because I started at the very first, and a subsequent agent that is positioned right next to it in the memory region, right? Because a PHP array is just element after element, like any C array or any other language. So it does so when I fetch my first element, I get cheap, or I get for free more than maybe one more element, two more elements, as many elements that the hardware can fit into this cache line. So in case I need to use the next element, I can already access it from the cache instead of going to the RAM. On this case, however, since I'm going vertically instead of horizontally, but the memory layout places my edges one next to the other as I'm adding them cell by cell, I am actually wasting or not taking advantage of this effort that the hardware is doing for me, and instead of using the first and second agent memory, I'm using the first, and then I have to go fetch from memory yet again from RAM the next element that I'm going to work on. When we switch this to going horizontally, then we are actually taking advantage of this advantage. So when I try to fetch, or when we're fetching the first element from RAM, again, the hardware takes as many elements as it can, subsequent elements as it can fit into the cache line. So the next time when I iterate to the next element and I request the next element, it's already at the cache and it doesn't go through the RAM. So clearly that has an impact on the performance of my application, because I have to do less stuff, or I have to go somewhere closer than the actual memory. And this is not precisely a new concept. This is a very old software that used to be part of DOS, and it was about trying to optimize an access to hard drive documents by making sure that the elements that are part of a file, of a document, that are these little blocks of bytes that actually compose a document are not all over the hard drive, because we write and then we delete, so stuff gets shuffled around. So on all hard drives, it was very painful to have to deal, particularly with large documents, because these little blocks were all over the place, and defrag would actually take those the block elements that are part of the same document as close to each other as possible. So when I'm reading a file, if I'm reading the first block of bytes and then I go to the next block of bytes, it's right there. It's the same essential concept. So this is not a revolution. Just thinking about how to optimize and how to take advantage of the cache or the stuff that the hardware is doing for me. Now, DoD takes, like we said originally, a completely different approach, in the sense that instead of focusing on the modelization of the problem, we focus on the data transformation. In our case, for our algorithm, the data transformation that we are working with is fairly simple. We have this world of agents again, and we go through those agents and we identify those enemies and those that I can beat, and from them all the arch enemies. So if I concentrate purely on that, I may instead of thinking about storing the information in a way that closely resembles in code what I see in real life, I'm just going to make sure that, or I'm going to focalize on making this process as efficient as possible. So I'm going to rethink the process of how I store stuff and how I fetch stuff, so it is as fast as possible. So in my case, since what we need is to identify enemies, and we identify enemies just by this little flag, this random flag that we added. Of those enemies, we identify those enemies that I can beat purely on the number of bullets. I obviously don't necessarily need all this extra information that is part of an agent, such as the name, all that extra set of bytes that I have a suspicion that is going to affect the way that I'm accessing the memory. So instead of simply storing the agents on this matrix and navigating that matrix, I create a completely different set of memory regions, where on one region I store only the enemies, one after the other, and on another region I store for those enemies the number of bullets they have. And I know, since every time that I add an enemy, I add its number of bullets, that the index on this array corresponds one to other. So when I find the number of bullets in element number 3, clearly the agent that owns those bullets is also on the index number 3 on the other array. And since I also know that one of the objectives of my process is to find the arch enemy, the enemy with the biggest amount of bullets, I also make sure that I optimize this other memory region where I store the bullets, so it becomes super fast to get the enemy with the most number of bullets, which is essentially sorting this array of sequential number of bullets numerically in descending order. So the one with the most bullets appears at first. And since AR sort, in this case, the sorting of the array in recursive order maintains the index in the array, I know that even though I just shuffle around one of the arrays and not the other one, the index that will hold the first element will point me to the right agent at the enemy's array. So now that I rethought the process of storing the information, adding data redundancy, again, another school of thought scene that we are taught that we should never do. By adding the redundancy, I know now that my logic to find the number of enemies and the arch enemy is going to be much more optimized, and it's going to look much more differently than our previous object-oriented standard way of thinking things. And on this case, I take, again, I am given the number of bullets that the player has, and I'm supposed to return the number of enemies and arch enemy, and I take advantage of these two different memory regions, the enemy bullets, and I go through all the enemy bullets. Since I know that I have to go through all the enemies, and I know that I have to, for those enemies, I need to know how many bullets in order to see if I can defeat them or not. Then I go through that array, one element after the other, and since that element is a memory region, is tightly and nicely packed, is clearly going to be beneficial. I also know that since the enemy bullets is sorted in descending order, the first enemy there, or the first number of bullets, belongs to the arc enemy. So the first element that I navigate that is actually a defeatable enemy becomes my arc enemy. It's one condition that I only that is a very cheap condition that I don't get to that I get to get the arc enemy very fast, and then I keep counting on the number of enemies, just because since they have bullets and I already know that I can defeat them, then they count towards the enemies. So clearly it's a completely different approach, in the sense that the business logic on the previous approach was hidden, particularly the business logic for knowing if an enemy can be killed or not was hidden and encapsulated in this interface method, is killable. And here, since I took a completely different approach and I didn't concentrate on abstraction, but I concentrated on data and performance and efficiency, that whole business logic kind of invaded the process. But it's considered to be an invasion just because we keep thinking that abstraction is the right way to go. Clearly, this is looking for taking advantage of the stuff that the hardware and the infrastructure that I'm working with has to offer me. And on this case, while as before, of course, the second implementation optimized and took advantage of the cache lines, I was still wasting a lot of bytes, because for that element that was loading into the cache into the cache. For that engine, I was only really using the number of bullets. I wasn't using the string. I wasn't using the position. So that was all part of the memory that was loaded into the cache and was being wasted because I didn't even use it. But on this example, since I decided to pack all the data that I'm actually going to be using on my process, I'm utilizing the whole space on the cache line available for me. So I get to process a lot more elements without going to the memory. And I know that it doesn't seem it doesn't seem that evident, because we are also taught that, why do we care RAM is so freaking fast, particularly now with DDR5 and all these improvements, that why is it so relevant to change my whole logic, and that was so neatly modelized and abstracted, just to make it faster and not reach RAM memory. One thing that is very, very eloquent when deciding if we should consider the underlying hardware is understanding the limitations of the underlying hardware. And the first time that I learned years ago about cache lines in CPU processes, I was quite impressed by the speed difference that it is compared to RAM. Something that we always consider to be the fastest thing ever, RAM, it suddenly becomes 20 times slower than what the CPU can provide. Of course, it's not the same of what I can achieve with RAM, because with RAM we may have a lot of more space, 64 gigabytes, such as thankfully the stuff that I have on this machine, while as cache lines are very, very much smaller. An L1 cache is I think 64 kilobytes, or no, it may even be slower, I don't know, I don't remember the numbers right now, but it's clearly limited for a reason, because it provides way faster access times than RAM, and that even worse than a solid state drive. So going for that 20 times improvement seems something to consider, particularly not only on the game development world, but for highly intensive processing algorithms. So in our case, we did this whole thing to supposedly take advantage of this ability to speed up using cache lines. Let's see how much of a difference it makes. I run the same script, it does the same thing. Obviously the numbers change, the number of bullets and all that change because of randomness, but I get a completely different scenario where this implementation is 69 times faster. That's 69 times, that's not 69%. 69 times faster than the previous implementation that was already optimized, and it's 109 times faster than Column, which is clearly, if this is a process that is very much a center of my application, which is on this very realistic case, this is clearly a massive improvement that is worth considering. It's that 3% that Donald actually was talking about when talking about premature optimization. So it's very, very interesting and a very beneficial effort that I just taken by modifying the way that I do things. Now, this may seem like it's not applicable to, or not applicable to a large scale. So, okay, I can get this, I can shave off a lot of resources, or I can speed up things dramatically. But how relevant this is really to our industry, our software industry, to actually warrant a rethinking process and moving away from established paradigms into this new data focused or data oriented world. So in order for us to put a little bit of perspective into how much of a major switch in effort and in focus this is for our industry, and the kind of impact that it may have all over the world, really, I like to use this, what it is arguably the biggest experiment of DoD development in the world. There's this company called Unity, that produces a game engine that game developers use to create games, but it's also used to be our source of media content and entertainment, movies even. That is a major player in the industry. It's one of the two biggest game engines, the other one being Unreal, and it actually recently went public, so it is a very big company. And it has such big impact that I think about 65 to 70% of all the games that are the biggest sellers on the App Store are made with Unity. There's a lot of movies that won awards that are made with Unity, or that had parts made with Unity. So there's a lot of stuff going on. There's a lot of people working on this tool. So a tool like this, revisiting or rethinking the way they do things in order to achieve performance improvement to a point where it actually may disrupt even the workload of someone that works with the tool. It is not an easy thing an easy challenge to actually take. So there must be a reason if they decided to actually go through this experiment of switching or embracing DoD at the core level. So in order to see the difference that it may make, or I wouldn't call it an experiment, because actually there's production code now running on this DoD approach or refactoring of their own engine. We need to understand how our own concepts that come from, again, established programming methodologies, object-oriented programming, apply to game development. In this case, this is a little sample scene that I normally work with when I like to play. It's been a while that I don't play around with game dev because of work, but when I play around, I normally have these little sample scenes to test stuff out. And I like this screenshot that I took because it clearly translates what we're seeing on our screen. These two little agents, one player and another agent that is not even there. How that translates into real OOP modelization, where I see on the left all the different elements that compose this model, having right hand, left arm, all these little things being objects. And since they are objects, they have a lot of baggage attached to them in terms of memory and in terms of processing code and a lot of stuff, where if I think about not having one agent but having several agents, then clearly the kind of performance difference that we saw in our little not realistic example can be also very, very noticeable in something like this, in an environment such as this that is supposed to run in way more limited hardware, such as consoles, PCs, or Nintendo Switch, or whatever. So that's the standard way of doing things in Unity, what is called Unity Classic, which is adhering to this OOP world, where this is each element of this model that I'm going to be attaching functionality to is obviously an implementation of a C# class in this case, because it's on C# that extends from mono behavior and adds these properties and attributes to that class that extend from mono behavior and adds this behavior regarding what happens when this hand collider goes through another collider. Should it create a sort of reaction? Should it send an event to the impacted mono behavior game object to produce some sort of reaction? So that's the standard way of doing things. That's the classic Unity way of doing things. So rethinking this process into a purely data-oriented approach implied completely rethinking the whole inner workings of their engine. Now, clearly they can't go and completely disregard classic and go straight to a completely new paradigm. So they had to work hard at making transition and making the necessary tools for developers to actually embrace progressively a more data-oriented approach and get the benefits of it without actually losing all the work and all the logic that they have. Now, they did so by creating this combination of things where it's not only about optimizing for memory and making sure that, like in our example, the memory is tightly filled where the elements that I'm accessing in the game are next to each other in memory, so I can take advantage of all the cache and all this stuff that the hardware allows me to use. And it's not only about that; it's also about rethinking the process and focalizing on data to get not only performance benefits because of the memory layout, but also performance benefits because we get to use multi-threaded code or even SIMD instructions on CPUs to do truly parallel processing by means of the job system. And it also went they went even further away, where they went at the low level, since they knew and they could now reason with the data, because everything is data oriented. It's not about an agent descending from a mono behavior and having an aggregation of body elements that are also descended from body behavior. It's about interpreting agents as purely references of data. An agent for me is an agent that when there comes a time where I need to deal with collisions, I'm only interested in the stuff that can collide with. So I don't think about working with agents. I think about working with elements that have the ability to collide with other elements, and I'm only interested in the data needed to process that. And we do so, and taking advantage of this rethinking of this constantly seeing entities as different snapshots of this or different subsets of data that normally would have been the entity data or the object data that would be all part of a single object. And now we're seeing this as merely snapshots that we're working with, the same way that we worked purely on the number of bullets instead of taking into account all the other stuff that defines an agent. The same way here on ECS, as they propose, the entities that we work with are simply snapshots of data that we are working with. And we work through that data, we transform that data by means of systems, or what they call systems, that take the kind of, or that actually allow us to query the data that we're looking for. Give me all the bullets, all the bullets that a person with or an agent that has bullets contains, and performing systems that work on that data, counting on our case, or maybe, I don't know, shooting or whatever else on another case, and having that ability to reason about the data, knowing that the data, and particularly even specifying if I'm going to mutate the data, if I'm going to change the number of bullets or not, allows their whole inner workings to be really smart about it and offer us multi-thread processing right from the get-go, because we're not only making sure that our code does or modifies or touches the right data, only the right data, but we are also making sure that there are no data collisions or data corruptness. So multi-threading becomes an even easier thing, and it is also guaranteed because of the way that this data is, or because of the restrictions that this ECS component system that Unity provides enforces on us, such as not having bool elements or other kind of stuff that may require managed heap or managed memory on C#, which is a major source of concern for game development, because managed memory means that at some point the garbage collector is going to come in and take a lot of time to clean up. Since by mapping or by working with data in this low-level way, completely removed from the managed memory space, we get a lot of performance benefits. And they took even this further, and they went down to a low level, and now knowing exactly how the data is mapped internally in memory, in hardware for each device, they were able to also modify the C# compiler and introduce the burst compiler, which translate some of the code in our systems, in the system that actually transform data from input to output into highly optimized machine code. Again, taking advantage of SIMD, parallel processing, and other stuff. So it was clearly a major undertaking that they are still going. It's been, I think, already 3 years that they went, if not more, that they went through this process. And they are still working on it. It's still not 100% bulletproof, and it's still very much a work in progress. But the benefits are as massive as we saw in our little unrealistic example. I took this from Jeremy, and where he made a simulation of the number of ants, or a number of ants. I can't remember now what the ants were doing, but just I'm pretty sure that just being there, like my little models, just standing there, not doing anything, the amount of memory that they take and the processing obviously becomes an issue when we start bumping up the number of ants to a point that we can see that at 5,000 ants, our game or our simulation becomes unrealistic because I'm not even reaching the minimum acceptable 30 frames per second that is characteristic of games, and not even the optimized and the more ideal 60 FPS. So by using the classic approach of standard object-oriented programming with classes descending from other classes and aggregation of attributes and all that, I lost the game or the ability to have a successful game at 5,000 ants. While as using this whole data-oriented approach, with the combination of the ECS, the burst compiler, and the burst compiler in Unity, we get a completely different scenario where we can go up to 100,000 and still have a very acceptable working game. 166 FPS, that's massive, and that is impressive. And that it means that I took a system that was completely broken at 5,000 and I took it and way up just by rethinking how the data is structured and is utilized in my system. So this is clearly not something to disregard as something that is purely hardware or performance details that are not relevant to our work. This is clearly affecting the whole industry. This something like this for something as impactful as Unity, that have so many games, so much media content out there, can have a massive impact. And just by, not just because obviously this was not an easy process, by rethinking the way we do things, by breaking assumptions. And it's not only obviously on the game development world that we've seen exercises like this of trying to reason about or seriously improve that 3% of stuff that is slowing things down. It's not only about the game industry. It happened all over our programming language ecosystem. It happened on PHP 7 when Nikita Popov, among others, completely rethought about how the way we store memory in PHP, particularly arrays, bringing a massive performance improvement of 30, no, not even, I think 40, 60, 50, 60% even in some cases, for code that didn't even have to change to take that advantage, just simply by focalizing on that area of the engine in this case that was dealing with memory and taking advantage of that. C# did it also, not only on the 8th version, but also on the 7th version, but it keeps going lower and lower towards the memory management to optimize as much as possible. And considering that Unity itself accounts for almost 60% of all the written C# code in the world, is also will also bring some very interesting performance improvement to an already established engine. Rust, with its own concept of static memory to guarantee memory safety, but also to make sure that memory is reasoned about right from the compiler stage. Also, there's a lot of work there in performance, and the JavaScript engines, Node, whatever, they all also went and keep going through this reimagining and rethinking memory and performance in general. But it's not just about memory. That's another aspect that normally gets neglected from DoD, that we normally reason about DoD at the low level hardware performance improvements, but it is mostly a way of rethinking our processes and not only thinking about actual RAM memory that we can optimize, it's about also optimizing or adding data redundancy to optimize our processes. On this case, this is an example that I had to, not an example, it's a case that I had to go through where we had this process where we create properties, we store properties that are from the real estate market on this Elasticsearch that has a lot of complex fields that I can query different ways, by proximity, by doing other kinds of filtering. And as part of that process that we had originally, where we process the property information and we store it on Elasticsearch, we also had to pre-calculate similar properties to subject properties. So we did that whole thing as the standard school of programming teach us on the same data store, because we already have it there neatly and data redundancy is wrong. So we did it on Elasticsearch, and we never thought about it much. We thought, okay, this is a process that works perfectly fine. But once we started seeing things differently and rethinking about our processes, we decided to start optimizing these areas that we assumed to be perfectly okay and not really needing performance improvements, such as, on this case, the fine comps area, which we accounted for as being the biggest load of time that was being taken when storing a property. We extracted that whole area of our code, and we introduced even a completely separate data set, completely redundant, because it contains similar information that is already on Elasticsearch, but it also contains a lot of redundant information to facilitate the calculation of finding properties. And just by rethinking this process or this use of our, in this case, our storage systems, we saw massive performance improvements. So this is not purely about improving hardware. It can go up and up in the layers of our day-to-day work. It may also mean that it's not about focalizing on data. It doesn't mean necessarily or purely thinking about storage, either memory or in actual storage engines. It could be even about what we do with the data that we process. I saw this example recently, a few days ago. It's kind of crazy, this NVIDIA video compression algorithm, where they are dealing with something that is very 2020 friendly, which is video streaming over the internet. And instead of going the standard approach of trying to narrow down the amount of space needed to transmit each of the frames that compose the movement of an image, or my face moving, or her face in this case moving, instead of focalizing or continuing on those assumptions that is the stuff that needs to be improved, they completely rethought about, okay, this is an input and output process. What about transforming the input, which is the image that is coming from the webcam, in a way that we produce the same output, but whatever we do in the middle could be completely different. So instead of thinking about compressing each of these keyframes, they thought, okay, maybe we just all that we really need is one keyframe to define the whole shape of car face and the surroundings, and then identify those points, or those key points in her face, in that keyframe, that are changing from one frame to the next. So instead of transmitting the different image changes, they transmit the movement of these key points, reducing considerably, and then recreating the image on the destination device, a mobile phone, a computer, or whatever, by using the standard neural networks or whatever, to produce the image back from those key points, considerably reducing the amount of speed needed to transmit this video. So it's not only about reducing memory, it's not only about reducing data storage, it may also be about rethinking our process and completely switching away from standard reasoning about performance. But it's also not just about performance. This whole approach of thinking about data first and thinking about modelization and coding as being purely an implementation detail of the data transformation can go, again, up the chain in our day-to-day. And I one of the best examples that I had to experience was a recent major refactoring that we had to do, where we had this system, selling a big number of product lines to customers with a lot of price points, different price points for different customers, tens of thousands of subscriptions. It used several payment gateways, and it had a lot of unknowns because the code was all over the place. Some of the payment code was part of the different product line source code, and some was on R2. So facing this refactoring with standard methodologies would have mean going into the code and try to choose the right architecture. Maybe it was DDD, maybe it was TDD or whatever. Looking into the code and trying to transfer that code that we're seeing currently working one way to our new and improved way, instead of thinking about and having to actually deal with even bigger problems that come with changing payment gateways, such as having to deal with the credit cards being transferred from one gateway to another, being PCI compliant. It was a whole mess that we really didn't want to go through this endless refactoring and following the established principles. And so instead we decided, let's just take a step back, do a little bit of what DoD says or teaches us, and think about purely the data, on the input data and the transformation and the output data we would produce with that transformation. And on this case, on our refactoring, we thought that the input data was nothing more or less than the customer credit cards, being one thing indistinctively from the other, a customer with a credit card. And the output that processing that this payment system had to do, this whole stuff of wibbly stuff, of complex stuff, it needed to produce recurring subscriptions that would get recurrently charged in different periods or fixed charges. And making no assumptions in the middle and how things were built before, and completely making sure that the only thing that we need to account for is producing the same data out of the same input as we were doing before, but in a completely different way. So we focus on data, we work on the transformation when we were doing that refactoring, and we made sure that it was efficient enough by challenging assumptions in our own code. And doing so in the process, we discover several things. We even discover complete unknowns that we had before, or situations with price points that we didn't even thought we had, because there were so much hidden inside that purely abstracted code that it was a very interesting take. So approaching change or approaching DoD doesn't have necessarily to do with purely hardware or purely performance or purely memory. It's about a complete way of rethinking our systems. It's about moving, like Nick says here, it's about moving from that ideal world where we keep thinking that the first thing that we need to account for when dealing with a software problem is what architecture we're going to choose. Instead of thinking that, we need to think about, like he says, going from A to B, which is a different way of saying data transformation, getting from A to B. So, and it's not only about rethinking our process and having no assumptions on the stuff that we normally work with, or the architectures we normally work with, even the programming language, or even writing code. It may even be about not writing code at all. It's about making sure that that we understand that the code that we tested is not necessarily, or that we assume to work, like in our payment refactoring, is not necessarily the right way, and it doesn't, and we would be following our wrong assumptions just by following that school of thought, and instead of focusing on the data, which is, again, as Mike said, our primarily and should be our only job, processing data from input to output, and making sure that data transformation is done as efficient as possible. So anyway, I'm certain that this is not the most deep down introduction to DoD. DoD has many layers of knowledge behind. There are several talks out there on YouTube that you should really check out. Not only, obviously, Mike Acton's several presentations are absolutely must see, but you also have Scott Myers and other prominent developers that are speaking about this. Again, this is almost exclusively coming out of the game development world, but it's starting to be seen on other areas. And I think that it is about time that even if we dedicate our time exclusively to web development, to rethink our own assumptions and start focalizing on the data and making the right decisions for a change. So anyway, I thought this time that the microphone didn't fail me and that this went through, and I'm going to be online while this is being streamed for any questions, and if you need to contact me after the streaming, that's my Twitter. That's pretty much the only channel of communication that I actually that I listen to. So if you need to reach out, there's the Twitter. And once again, thanks for everyone in the organization of CakeFest. Again, massive undertaking. Congratulate you all. And I hope that 2021 we get to do this again, but this time in real life, somewhere around the world.